Okay, today we're going to take a look at one of the biggest theorems that there is in geometry. It's called the Pythagorean Theorem. And so let's take a look at it. It's named for a Greek geometer named Pythagoras, although it wasn't actually his. He just had a school and it was attributed to him. But here's the Pythagorean Theorem. All right. In a right triangle. So it only works for right triangles. But if you have a right triangle, the length of the hypotenuse squared is equal to the sum of the squares of the lengths of the legs. Now that is the Pythagorean theorem. Let's read it one more time. In a right triangle, the length of the hypotenuse squared is equal to the sum of the squares of the lengths of the legs. Now, in most instances, we will have a right triangle drawn, something like this. And the side lengths we'll use with lowercase letters, where the legs are A, B, and the hypotenuse is side C. The hypotenuse is only for a right triangle. It's the biggest side of a right triangle. And it's always opposite this 90-degree angle. Here's what that Pythagorean theorem looks like in formula. C squared, that's the square of the length of the hypotenuse, is equal to the sum of the squares of the lengths of the legs. All right? And this is what we call the Pythagorean theorem, the formula for it. The theorem is actually the words. This is the formula. So let's take a look at some examples that we have on how to actually use this Pythagorean theorem. Take a look at example 1 on page 427. Now this starts with two side lengths of 6 and 8. The 8 is on the horizontal part, the 6 is on the vertical, and we have the right angle between them. So we're going to call the hypotenuse C, which we always will. They're using X, we're going to use C. And we're just going to write the formula down. C squared is equal to 8 squared plus 6 squared. That's the sum of the squares of the lengths of the sides. Well, we have to go through and multiply these out. Well, again, these are both from our multiplication tables, so those are not too bad. And then when we add the 64 and 36 together, that's 100. But again, that is C squared is equal to 100. Well, if C squared is 100, what number multiplied times itself equals 100? Let's take the square root of both sides. So here we go. The square root of C squared is equal to C, and the square root of 100, that's a 10. So the side length that we have here for C is 10. The legs, small, medium, large, 6, 8, and then finally hypotenuse of 10. Take a look on page 420, what is that, 7? 428. 428. Look at the example 2. It says a 16-foot ladder rests against the side of the house and the base of the ladder is 4 feet away from the bottom of the house. Approximately how high above the ground is the top of the ladder? Well, now you can see from the diagram that they have this set up, and the ladder's length we know, right? That's 16 feet, and that's what's laying up against the house. We'll put it right here. So there's the ladder, that's 16 feet. Well, how far is the base from the bottom of the house? Well, that's 4 right here. And what they're asking is, how high up on this house is this ladder reaching? In other words, what is this distance from here to here? Well, I'm just going to pick the side length and call it B, because that's what I don't know. The textbook can use X if they want to, but we're going to go through and solve for that height. Well, now here's where some people go through and mess the formula up. It is c squared, the hypotenuse, is equal to the sum of the squares of the legs. You don't get to write 16 squared plus 4 squared is equal to b squared, all right? Because 16 is the length of the hypotenuse. So we have to put it over here by itself first, and then the a is 4, and then b squared. Now then, multiplying these out, 16 squared is 256, is equal to 16 plus b squared. Subtract 16 from both sides, we get 240 is equal to b squared. Now, we've got b squared by itself. We need to take the square root of both sides. So let's do that. Now, on the right, this is going to give us b, but what is the square root of 240? If all we need is an approximation, then we can go through and just punch it in on our calculator. In fact, you can find that button on most of the TI-84 models right above the square for x, second x squared, and that'll give you the square root of that. But if it asks for the exact value, and often it will, we need to go through and find any perfect squares that are factors of 240. Well, let's just see. How does 240 factor? Well, a couple of easy factors of 240 are 10 and 24. All right, it ends in a 0, so we know that it's divisible by 10. 10 factors to 2 and 5, neither of which is a perfect square. But now 24 does have a perfect square. We can break this not as 3 and 8 or 2 and 12, but 4 and 6. And then the 6 breaks down to 2 and 3, and the 4 breaks down to 2 and 2. So the prime factorization of 240 is 2 times 2 times 2 times 2, or 2 to the 4th power, times 3 times 5. There is our prime factorization. But look at the exponent on the 2. It's an even number. In fact, when we look at this, 240 is equal to, well, 2 to the 4th is 16. Times, I'm just going to multiply the 3 and 5 together because they are not perfect squares. 16 is a perfect square. So when we're looking over here on the left, the square root of, I'm going to put the perfect square first, 16, and then the times 15. Those are the two factors that we want, because 16 is the largest perfect square that's a factor of 240. Now then, we can take these, because it's a multiplication, and separate it as the square root of 16 times the square root of 15. And the square root of 16 comes out as a 4. 4 times the square root of 15 is equal to b. And that is the exact height of that ladder up on the wall. And anytime it asks for exact values, this is what we want to use. Now, we have right triangles, and a lot of times people who are working with these triangles, they want to use integer values for the side lengths. Well, we have certain triangles that fit into these, and so let's call these Pythagorean triples. They're integer values that fit the Pythagorean theorem. Well, we have certain ones that we're required to know what they are without having to go through and use the Pythagorean theorem every time to calculate them. So here are what we're going to call as the primitive Pythagorean triples. 3, 4, 5. This is the smallest right triangle that has integer values for its side lengths. Now, primitive because this is the simplest one, but we can take multiples of a 3, 4, 5, say 6, 8, 10, if we multiply by 2. In fact, the very first example that we had in this section, example 1, had two side lengths of 6 and 8. If you knew the Pythagorean triple, you wouldn't have to go through all those steps with the Pythagorean theorem. You just say, oh, well, it's got to be 6, 8. Those are both divisible by 2. That's a 3, 4, 5 triangle. All the side lengths have been doubled. And again, this works. We could multiply by 3. We could have a 9, 12, 15. Or multiply by 7, 21, 28, 35. Okay? All that we need to look for are, is it a multiple of the original 3, 4, 5? Well, the second Pythagorean triple family that we need, its primitive Pythagorean triple is a 5, 12, 13. This is followed by a 7, 24, 25. And then finally an 8, 15, 17. Well, I'm just going to put some other triples that fall in these families. 5, 12, 13, 10, 24, 26. Doubling is very, very easy. It happens often. For the 7, 24, 25, again, you'll see this doubled often. 14, 48, 50. The side lengths don't get too large when you go through and you just double. For an 8, 15, 17, suppose we were to triple. This would be a 24, 45, and then 3 times 17, 51. All right, that's still in the family of the 8, 15, 17, and since the 8, 15, 17 is the primitive, we're just looking for multiples of these. Now, on the bottom of page 429, they have an entire list of each of these. And notice on that bottom row for each of these, they're saying any of the families, the 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, each of these, if you have a common factor, like 3x, 4x, 5x, x is common. And so really all you're looking for, do I have any common factors between these? All right? So these are the Pythagorean triples, and these are the ones that we want you to know automatically. We don't want you to have to use the Pythagorean theorem. That's fine if it's not integer values, but for these triangles, which occur very, very often, especially in standardized tests, even previous chapters in this textbook, now that we know what a Pythagorean triple is, if you were to go back and look at the right triangles that were listed, so many of them are these Pythagorean triples. And again, that's because most of the time people like working with integers instead of decimals or fractions. And so it's much, much easier to use these types. Now, there are an infinite number of Pythagorean triples. This is definitely not all there are. But these are the smallest ones that come up a whole lot. When you get into others that are bigger, well, then the side lengths get just so big that very few people use those, although they exist. We'll show you a pattern on the first second, and third, these first three right here, and show you how there is a pattern, one pattern, 3, 4, 5, and then right down here beneath it, I'm going to go 5, 12, 13. Move this up just a little bit. And then directly beneath here, 7, 24, 25. And what I want to do is I want to look in the small, medium, and large positions for any kind of a pattern that I might be able to find. Well, the first one, from 3 to 5, well, that's just adding 2. 5 to 7 is adding 2. So maybe if we added 2 again, maybe that would work. We'll just try it and put a 9 right here. Well, look in the second column, from 4 to 12. Let's see, that's plus 8 right here. From 12 to 24, that's plus 16. And so, let's see, 12, that's 8. Well, actually, that's 12, not 16. That makes it work a little better. So maybe if we just added 8 plus 12 plus 16, let's go plus 16 right here, and make that a 40. Well, now then, look at the second and third positions. Notice that the 4 is exactly 1 less than 5. 12 is exactly 1 less than 13. 24 is exactly 1 less than 25. And yes, this one as well, the longer leg, is exactly 1 less than the hypotenuse. So it's a 9, 40, 41. This pattern continues. There are many more in this series, but notice that the 8, 15, 17 Pythagorean triple, it's there. It just doesn't fit this pattern. And there's lots of other Pythagorean triples that don't fit this pattern, but they're there. All right? But again, the ones that we need to know, this one, this one, this one, and this one, and their multiples. That is the Pythagorean theorem.